Okay, look around you right now. The chair you're sitting in, the walls of your house, even your own hands, they all feel incredibly solid, don't they? Well, what if I told you that solidity is basically a huge illusion? Welcome to today's Explainer, where we're going to act as scientific detectives. We're going on a journey to uncover the microscopic architecture of our universe and, frankly, explore one of the most massive paradigm shifts in human history. We've got to start our investigation with a question that is incredibly simple but totally mind-boggling. Imagine taking a piece of clay. You cut it in half, then you cut that half in half, and you just keep going. Do you eventually hit a wall? Like, is there a fundamental, unbreakable building block at the absolute foundation of reality? This isn't a new question, by the way. Way back over 2 millennia ago in ancient India, a brilliant thinker named Acharya Kannada suggested that if you kept dividing matter, you'd eventually hit indivisible particles. He called them parmenus. Right around the same time, ancient Greek philosophers like Democritus were having the exact same thought, calling these unbreakable pieces atomos. But, for centuries, this was just philosophy. It was just a really cool thought experiment. It actually wasn't until 1808 that a guy named John Dalton turned this into a real scientific theory. Dalton firmly stated that all matter is made of solid, completely unbreakable atoms. And honestly, that is the absolute beauty of scientific exploration. Dalton's model wasn't entirely right. Actually, it was pretty wrong in some big ways. But it shows us exactly how science moves forward. It's one step at a time, driven by just pure curiosity, questioning everything, and rigorous experimentation. In science, even our incorrect answers are absolutely crucial stepping stones. Dalton's unbreakable atom was a perfectly logical starting point, the very first real clue in figuring out how our universe is actually built. But then, we hit a massive plot twist. Just when the scientific world was feeling pretty good about atoms being these solid, indestructible little spheres, the late 19th century rolled around. Researchers started stumbling upon some deeply weird stuff, things like radioactivity and cathode rays. Suddenly, they were watching atoms spit out invisible energy and particles. This literally shattered centuries of dogma. It proved, without a doubt, that the atom wasn't the end of the road at all. The atom actually contained its own secret, microscopic world of even smaller parts. Fast forward to 1897, and a physicist named J.J. Thomson basically cracks the atom wide open. He was messing around with a cathode ray tube, basically running high voltage through trapped gases at incredibly low pressure. He gets this glowing beam, right? But by testing it with magnets and electric fields, Thomson figures out this isn't just weird light. It is a stream of tiny, negatively charged particles. He had literally just discovered the electron. And the craziest part, because he saw these exact same electrons no matter what gas he used, he proved they're a fundamental building block of literally every element in existence. Absolute game changer. But here's the thing with major breakthroughs. They usually just create bigger problems. Thomson's discovery immediately sparked a massive, head-scratching puzzle. Think about it. We know atoms are electrically neutral overall, right? Your coffee mug doesn't randomly electrocute you when you pick it up. So if these newly discovered electrons are carrying a negative charge, where in the world is the positive charge hiding to balance it all out? This single mystery forced everyone to totally rethink what the inside of an atom actually looked like. Thomson's answer to this puzzle was pretty creative and honestly kind of delicious. He suggested thinking of the atom like a watermelon. Imagine the red, fleshy pulp inside is a continuous spread of positive charge. Then, the tiny negative electrons are like the black seeds, just randomly suspended and stuck inside that positive pulp. It was a really brilliant first attempt at explaining how those electrical charges stay perfectly balanced inside an atom. But you know how it goes. Every great theory has to survive being tested against harsh reality. So in 1911, Ernest Rutherford and his team, specifically Geiger and Marsden, set up this incredibly famous gold foil experiment. They fired a beam of incredibly fast, positively charged alpha particles at a sheet of gold foil that was insanely thin. Now, because they believed in Thomson's watermelon model, where the positive charge is basically spread out and weak, they totally expected these fast particles to just punch straight through. But the reality? No way. While most did go straight through, some violently sharply deflected, and a few actually bounced right back at the emitter. Rutherford himself later said it was like firing a massive artillery shell at a piece of tissue paper and having it bounce back and hit you. Okay, so based on this shocking data, Rutherford sits down and systematically draws up a revolutionary new blueprint for the atom. First, because almost all those particles zipped straight through, he realized that the vast majority of an atom is actually completely empty space. Second, those rare particles that ricocheted back,
They had to have hit something unimaginably dense and positively charged, right dead in the center. He called this the nucleus. Finally, he figured that negative electrons must be flying around this tiny nucleus, kind of like planets orbiting the sun in our own solar system.
Now, we really need to pause and grasp the sheer, mind-blowing scale Rutherford calculated here. This central, dense nucleus, it is about 1 lakh. That's 100,000 times smaller than the overall atom itself. Let's put that into a real-world perspective to show you just how wild that is. Imagine if a single atom magically expanded to be the size of a massive 100-meter cricket stadium. In that giant arena, the ultra-dense nucleus would be the size of a single tiny grain of black pepper, sitting right on the center pitch. The rest of the entire stadium? It's almost completely empty space, with these microscopic electrons just zipping around the very outer boundary. It literally redefines what it means to touch the solid objects around us every single day. If you want another crazy way to comprehend this microscopic reality, let's think about how many atoms it takes to make something you can actually see. Grab a standard sheet of paper. It's only about 0.1 millimeters thick, right? Well, it would take stacking 1 million atoms directly on top of each other just to match the thickness of that single page. Think about that the next time you're reading a book. There is literally a bustling universe of tiny planetary systems contained within a fraction of a millimeter. So when we pit these two ideas against each other, you really see the massive leap science took. On one hand, you have Thomson's watermelon model, this soft, continuous blob of positive charge with electrons just resting inside. And then bam, Rutherford's planetary model completely flips the script. Suddenly, almost everything is empty space. All the positive charge is locked into this incredibly tiny, ultra-dense vault in the center, and electrons are dynamically flying around in the void. It was a total paradigm shift. And Rutherford wasn't entirely done. He eventually figured out why that tiny nucleus is positively charged. It's filled with subatomic particles called protons. Now, protons are absolute heavyweights compared to electrons. They hold almost all of the atom's total mass. And having perfectly equal numbers of these heavy positive protons in the center and those super light negative electrons zooming around the outside, well, that's exactly the magic trick that keeps an atom electrically neutral and stable. But hold on a second. Our scientific detective story isn't quite wrapped up nicely with a bow just yet. Rutherford's planetary model is brilliant, sure, but it actually has a massive, fatal structural flaw. According to the absolute laws of physics, if a negatively charged electron is constantly changing direction to fly in a circle around a positive nucleus, it has to be bleeding off energy. And if it's continuously losing energy, it should quickly spiral inward and crash directly into the nucleus, totally collapsing the entire atom. But atoms exist, we aren't collapsing into nothingness. So how on earth do electrons defy the laws of physics to keep matter stable? I'm going to leave you with that massive structural mystery. Because in science, solving one incredible puzzle almost always uncovers another, even deeper mystery just waiting to be explored.